EE211, Circuit Analysis 1, Chapter 4. So, overview of this chapter, we will introduce superpositioning principle for linear circuits, some simplification techniques, source transformations they'll be called, and then also Thevenin and Norton theorems, so you can make more equivalent circuits just like we did for delta and y. So, and then at the end of the chapter we have some applications. So the first concept is the concept of a linear circuit. Linearity in a circuit means that if you change the current, the voltage will change proportionally, not as a square, not as some polynomial function, but current changes and voltage changes proportionally. It also requires that the circuit responses to the sum of the sources will be the same as if you did each source individually. So resistor circuits satisfy both of these criteria. So let's see, what does it mean to be if a circuit is linear? Equation form of what I just said is that if I multiply the current by some constant amount, the voltage will also proportionally increase. So as a direct consequence, if I have two currents summed together in a particular branch in the circuit going through one resistor, that's the same as current 1 going through the resistor plus current 2 going through the resistor, which is the same as voltage 1 plus voltage 2. So I'm going to show you this all by example. So linear circuit is additive. Here's my additive example, and homogeneous. So homogeneous has several different meanings, but basically it means that everything is essentially alike. In mathematics, you can have a common property, like a homogeneous figure might be all of one solid figure. Math equations have are homogeneous if they're all of the same degree, like all squared or all cubed or all x squared y cubed. So this example right here is a homogeneous equation of degree 5. And there's also a differential equation interpretation in which the linear combination of the derivatives is set equal to 0. I don't think anybody yet has to worry about definition number 4. But more math is good. So superpositioning principle. As a consequence of being a linear circuit, that means that we can turn off one source, find what's happening in the circuit, then turn off the other source, and then find out what's happening in the circuit. So basically, in the official language, if there are two or more independent sources, then there are two ways to solve for the circuit parameters. You can do the nodal or the mesh analysis like we've been doing in the previous chapter, or you can use a superposition principle. So basically, this is the principle stated right here, but I think it'll be more apparent when we work through the example. So applying superposition. Superposition means you're going to have one independent source on at a time. You're going to analyze the whole circuit. Then you're going to turn off the first source, turn on the second source, and analyze the circuit a second time. And then you're going to add up the results. So it's like a particular resistor is affected by one source, and it's affected by the other source. And you can analyze the circuit with one source on at a time. So steps are: turn off all the independent sources except one. So by turning off, that means you either short circuit a voltage source or you open circuit a current source. So short a voltage or open a current source. Then you find whatever output you're looking for, voltage or current, that's due to the active source, using the same techniques we did in chapter 2 and 3, which is KCL or KVL. You must leave the dependent sources on when you do this analysis. So you don't turn those off because they depend on some other part of the circuit. So you repeat that process, and then you sum up the individual combination algebraically from the different independent sources. By the way, this principle of superpositioning, although it's nice and it's a good example of what linearity means in a circuit, it usually involves more work than just doing KCL or KVL to begin with. So let's do an example to illustrate the superpositioning principle. So I am going to need to find the voltage that's across this resistor. So part of the voltage will come from the contribution from this source, and part of the voltage here will come as a contribution from this source. So this V that's across this resistor that I need to know has a contribution from the first source, which that's that source. So it's not, this isn't V1, but it's the contribution. V1 is the contribution from this source, and V2 is the contribution from this source. So the first step says you turn off one of the independent sources. I am going to turn off this current source. So when I turn off the current source, that means to open circuit it. So you see it's an open circuit, and if something is an open circuit, it's just not in the circuit anymore. And then I can analyze this circuit using the means that we had in the last two chapters. So this looks like a KVL to me. And I'll write KVL around the loop. So -6 plus, just put my signs on here. That's a minus. -6 plus I times 8 plus, make sure that's I1. Here, let me erase that, just to be consistent. I1 because it goes with V1, I1 times 8 plus I1 times 4 equals 0. So I did KVL around the loop. I get 6 equals 12 I1, or I1 equals half a amp. And so since I know I1, I can find V1. V1 equals I1 times 4 ohms. So V1 equals 2 volts. So we have that 2 right now, 2 volts for V1. So second step is now turn off the voltage source. Turning off a voltage source means to short it. So I have shorted it out, and turn back on this source. So I want now to find a contribution to this source. When I see current sources in the network, I think KCL. And so I'm going to write KCL at this node right here. This, I called it VA, but let's really call it V2 because it is right now V2, right? So 3 goes into the node, I2 goes out of the node, and I3 goes out of the node. So 3 equals, what can you say I2 is? V2 over 8 plus I3. I3 is V2 over 4. Multiply both sides times 8, I get 24 equals V2 plus 2V2, or V2 equals 8 volts. So plus 8 volts. So I find out that the voltage, this voltage in the resistor, it gets 2 volts contribution from here, 8 volts contribution from here, and the total voltage there is 10 volts. I'm going to do another example. This one actually is in your textbook, so it's already worked out in your textbook. But I think that I would like to do at least talk about an example that's a little bit more complicated. The circuit comes out of your book. I don't remember if they solved it or not. But I'm just going to set it up. So in this example, you want to find the current going through this 5 ohm resistor. So the contribution to the current comes from this independent current source and this independent voltage source. Since I want to find the current, I'm going to do it as a sum of currents going through this branch right now. So I will call I0 being the contribution from this source, and I0 prime that is, and I0 prime prime, or double prime, being the contribution from this source. So step 1 will be to turn off one of the sources. I'll turn off that 20 volt source, which means to short it out, and then I will analyze this problem. Notice I have left the dependent source in there, but the current, up here it's 5I0, so this dependent source is 5 times, the voltage of this dependent voltage source is 5 times the current here. But right now I only have I0 prime in here, so the dependent source now is 5I0 prime. Then I can go ahead and analyze this circuit with either KCL or KVL. Either one will work, and solve for I0 prime. The next step is to turn this source back on, put it back in the circuit, and then turn this one off. When you want to turn off the current source, that means open circuit it. So I open circuit it, and then I analyze this circuit again using the techniques we already know. But again, the dependent source stays here, only now it's dependent on the current in this branch, which currently in this circuit is I0 prime prime. So I write it that way appropriately. So the rest of the problem is just tedious math, but I wanted to at least go over setting it up. So superpositioning is a nice illustration of linear circuits to me, but it isn't always the best way to solve a circuit or to completely analyze a circuit. So the next section here I'm talking about are ways that help you to simplify the circuit. So remember when we did the delta Y transformation, it's because you wanted to make some kind of an equivalent circuit so that you could analyze the rest of the circuit. So this is the same reason that we do transformations on our sources, that is our current sources and our voltage sources. So it's a way for simplifying the circuits, and this is especially true when you have circuits that have both current sources in it and voltage sources, like the problems we just did. So anyways, proceeding on. So basically, if you have a part of your circuit that has a source and a resistor, you can transform it equivalently to a current source and a resistor. These are in parallel, series, and this one's in parallel. Similarly, if you have a current source in parallel with a resistor, then you can transform it to a voltage source and a resistor. This is really a consequence of Ohm's law, but let me show you a little bit more about that. The reason they're equivalent is because if I was looking at their terminals with my voltmeter or my current meter, my voltmeter or my current meter, I would see the same thing happening between terminals A and B. And I will show that to you in a minute. So in one case, if the sources are turned off, remember what turned off means, the resistance will always measure the same if the two circuits are equivalent. And then if the terminals are short-circuited, the currents will always be the same for the circuits. So basically it looks like a consequence of Ohm's law. But let me show you. So here I have a circuit that's open, and I can see the voltage between A and B. That's an open circuit voltage. So I'm going to say V open circuit, OS for open circuit, is what? It is simply V source. So if I use my voltage meter and I measured the voltage right here, I would just see the source voltage. Now, if I short-circuited it, I short circuit, what would I short circuit be? What is the current in this loop right now? You should be able to, by inspection, say that it's Vs over R. So that's what the short circuit current is. So this, I claim, is the equivalent circuit. So I can't tell what V open circuit is right now because any kind of voltage can be here. Oh, yes, I can tell what voltage would be here. What voltage would be here? I have the same current in the loop. So V open circuit is Is times R. Is the I of the source times R. And I short circuit, so if I shorted it out now, I short this out, I short circuit equals Is. So if I look at these two as being equivalents, I get right here that Vs equals I short circuit times R, and down here I get the V is I times R. These are S's, not phi's. So if I were to measure voltages and currents at either one of these terminals, I am going to get the same thing. They are equivalent circuits. Equivalent whether you short it. If you short it, I'll get the same current. And if I, because here, so if I open it, I get this voltage, which is the same as this voltage. If I short it, I get this voltage, which is the same as this voltage. So they are equivalent. You can also do the same thing to dependent sources, but be careful. Just do it carefully. Pay close attention to the orientation, whether the plus sign is up here, make the arrow go up here, and then you can still have the equivalent relationships. So note, special notes. Note that the arrow of the current source is directed towards the positive terminal of the voltage source, right? Arrow up is directed the same direction the plus sign is. There is a note about source transformations are not possible for an ideal voltage source. So that's because R equals 0 in an ideal voltage source. So you cannot do the source transformations then. So realistically, voltage sources have some internal resistance, and realistically, current sources also have some resistance. But in the ideal world, they have infinite. They don't load down the circuit, right? Okay, so I was going to do an example of that, and I decided not to do the example that was already worked out for you in the textbook, because you can work that problem out for yourself. So I'll do one of the problems that they give an answer for, but they don't work the problem out. So this is it. The problem is to find I0 in the circuit. And so I look at this, and there's a couple of things that I can see right off just to start simplifying it. The other thing that I recognize about this circuit is that if I can find the voltage at this node, then voltage divided by 7 ohms will give me I0. So ultimately, I think I'm going to want to find the voltage at that node. But some simplifications that occur right away. These are parallel resistor or series resistors, and that's 5 ohms. The other thing that I see is that this resistor, this 7 ohm, is in parallel with this 5 ohm. So I'm going to start redrawing this circuit. I'm going to put my current source right here. That was 3 amps. And then there is no reason why I cannot move this resistor on this side over here, correct? No reason whatsoever. That's still in parallel, that still has the same whatever voltage is across it. So I really have over here the 7 ohm being in parallel with the 5 ohm. Likewise, on this part of the circuit, this is one whole node, and this is one whole node. And this 6 ohm is really in parallel with 3 ohm. I'm just going to draw it like that. So that's 5 amps. That's 6 in parallel with 3 ohms. And it turns out if I do that calculation, 6 times 3 over 6 plus 3, that's parallel 2 resistors, 18 over 9, which will equal 2 ohms. And then this parallel combination over here, 7 in parallel with 5, equals 7 times 5 over 7 plus 5, which equals 35 over 12 ohms. So I'll go ahead and redraw that circuit now that I've simplified it a little bit. Now for me, it helps me to redraw circuits several times in the process. Otherwise, I'm likely to make a mistake. But maybe some of you are smarter than me and you don't redraw your circuits, but I do. Helps me make less mistakes, and I make enough mistakes as it is. We all do. What was the value of that current source? 3 amps. And this is now 35 over 12, which happens to, well, we'll just leave it at 35 over 12, because that's exact, right? Okay, so now the circuit looks a little bit more manageable, but we want to apply a source transformation, and the one that looks really obvious to me is that I can convert this into a voltage source in series with a resistor, and I can convert this one to a voltage source in series with a resistor. So let's do that. I will have a voltage source. Arrow is up here, so I'll put the plus sign up. A voltage source here that will equal, the V will equal I times R, so it will equal 10 volts. And the R is still 2 ohms. So I transformed that guy. I still have my minus plus 5 volts here. And I will transform this guy. Whoops, I don't want to. I will transform this guy also. It will be a resistor with a value of 35 over 12 and a voltage source, minding my polarities. And that voltage source will be 3 current times resistance, 3 times 35 over 12, which will be 35 over 4 volts. Ohms. Okay, so now I see a single loop, and now the circuit becomes a lot easier to analyze. I can find my 1I in the loop, so I'm going to go around the loop, put my arrows on, make my assumptions here. Minus 10 plus 2I minus 5 plus did I make a mistake here? Let me check here for a second. No, it's I had to think for a minute. We are good. So plus 35 over 12 I, and then coming around the loop, plus 35 over 4 equals 0. So I go ahead and do the algebra problem here, solving for I, and I will get I equals 1.2712 amps. So now I have this current in the loop. At this point, I can find out what the voltage is right here. So remember, that voltage right here is that same voltage that's right here, and it's the same voltage that's right here in the circuit, this node, right? So, because it's right here, rearranged, and now in this circuit, it's still up here at the top, this voltage up here, which is the same as this voltage right here. So these are the same voltages. And then if I know that voltage right at the connection to the 5 volts, then I can find the current that was in that original 7 ohm resistor. So I can find the voltage here. It's this voltage plus I times this resistor, right? So that voltage at that node, I don't know what I want to call it, V. I'll call it V what? V0, because it's the same voltage that's associated with the current that we're trying to find. V0. V0 equals 35 divided by 12, which happened, or 35 divided by 4 right here, which actually happens to be 0.75. So it's 35 divided by 4. That voltage plus I times that resistor plus I times 35 over 12. And you put I in right there, and you will have that the voltage at that node will end up being 12.45767 volts. And if I look back at the problem for a minute, I now know that I have 12 point whatever volts right here. I have 7 ohms, so I can find out what that current is. So I0 equals 12.45767 volts divided by 7 ohms, and I will get the answer of being 1.78 amps, which I do believe was the answer that the textbook gave, which means I did the problem right. There it is. The answer is 1.78 amps. So that's what I got. The book didn't solve the problem for you, but I went ahead and did it.